Just to do a little housekeeping, there's a question tab on your panel, and please feel free to enter any questions that you may have throughout the webinar in there. At the end of the webinar, I'll make sure to take some time and answer any questions that you may have. Also, a recording of this session will be on our Exida YouTube station and the Exida website, and you will be emailed a copy of the slides later this week. So today we're going to talk about what is a systematic failure and what is a random failure. Functional safety standards distinguish between systematic and random failures. The definition attempt to clarify how to categorize real failures. The standards also explain that random failures are included in probabilistic failure analysis, and systematic failures require changes in operating procedures. We'll go ahead and look at the different definitions between the functional safety standards, see what is black and white and what's a little gray or fuzzy in the middle. We will look at all real failures and how they may prevent a safety system from performing its safety protection, and how field failure collection system must account for any real failures until it's shown by a new failure record that a change in the procedure is effected, eliminating that type of failure. We're going to also look at some real-world examples and talk about if it is a random failure, if it's a systematic failure, and we're going to go through examples and actually do a poll, a couple of polls, to see what your answers are and compare them to a survey that we sent out to see what other people's answers were. And we'll go through each question and pull it apart, why it would be considered random or systematic. My name is Lauren Stewart. I went to Virginia Tech in mechanical engineering. I started my professional experience in custom design and manufacture, and now I'm here with Exida as a safety engineer for their mechanical customers. Along with certification, I also do research in stiction and mechanical failure rates. We have locations all around the world. We like to see, no matter where you are or your customers are, we have somebody close by in Exida that can help you. We found a global market research company report by the ARC advisory group that was conducted in November of 2015, and we were really excited. We found that more than half of the safety device certifications in the process industry were done by Exida. We were a little bit surprised by those numbers, but we were really excited to see the market recognition. We have engineering tools to help our end users out. We have an alarm management tool, we have a PHA tool, SIL selection, an SRS, a SIL verification, a proof test specification, and a data collection tool called SIL Stat. We have a bunch of different reference materials in the format of textbooks and internet books. We try to be a completely transparent company. That's why we do a lot of the webinars and blogs. So any research that we've done, all of our process for certification, everything is referenced and explained in our different textbooks. So we try to make sure that we don't hide anything. We want to be transparent so you know everything that we're doing and all of the research that we're doing. We are broken up into different main products and service categories. We have our consulting, our engineering tools, our product certification, our training, our reference materials, and our professional certification. So we like to say if it has to do with functional safety, no matter if it's the process, the products, or the people, we work in it. So today we're going to talk about the definitions of random and systematic failures. We're going to look at some real failure examples and field failure data collection and why all of this is important to you. Many engineers classify real failures as systematic and therefore eliminate them from their failure count, which is fine if they are truly a systematic failure. But if they're not, their then failure rate could be very misleading at best and possibly even dangerous. And that's why we wanted to do this webinar today. We want to make sure that we tell people that all real failures must be counted in any failure rate data collection system until it is proven that the change has been made, that the failure is no longer going to be occurring again per the failure data, whether that was a procedural or a design changes, and that's completely eliminated the issue or the systematic failure. This all comes to play where we take a look at end users' field failure data studies. And these data studies are an absolute rich opportunity to obtain site-specific failure rates and failure mode information about a specific problem in a specific application. But there are some problems when companies compare their end-user field failure data studies to each other's. First of all, a number of companies have either an insufficient information on their field failure reports, or they have different data collection analysis methods, and they have different definitions of what is a failure. Some companies would take the exact same failure in the exact same application, and one company would say it's random and one company would say it's systematic. And because of those, the end user field failure data studies are getting a little bit of a bad rap. But that's not what we want to portray. We want to show that there could be very valuable information in these data studies. However, you need to know all of the things to look for when you incur one. So the first thing to understanding random versus systematic failures is looking at the actual definitions from IEC 61508. And both of these definitions were pulled from the latest IEC 61508 standard, which was updated in 2010. They define a random hardware failure as a failure occurring at a random time which results from one or more of possible degraded mechanisms in hardware. Okay, well, that doesn't really tell you very much. So we can understand why random failures are a little confusing. When you look at the definition for a systematic failure, it does tell you a little bit more information. A systematic failure is a failure related in a deterministic way to a certain cause, which can only be eliminated by a modification of the design, or of the manufacturing process, or the operational procedures, or some kind of documentation, or other relevant factors. So it's a lot easier to understand what a systematic failure is from this definition than the random failure, but it's still not cut and dry. So this tells you that A, the failure has to be related in a deterministic way, and B, you have to make a change to something for it to be a systematic failure or to undo another systematic failure going to occur in the same way. So we can understand where it gets a little blurred, where if it would be a random or a systematic failure if you're just looking at these definitions. There's often times that the definitions are not mutually exclusive, or they've really confused a lot of people when they just read this. So the new edition of IEC 61511 actually has just been updated in 2016, and they improved the definition of a systematic failure. And it now reads, a systematic failure is a failure related to a pre-existing fault which consistently occurs under a particular condition and which can only be eliminated by removing the fault by a modification of the design, of the manufacturing process, of the operating procedures, the documentation, or other relevant factors. So that still, you have to change something in documents or procedures is still there in the systematic definition. But the beginning of the definition in the 61511 explains what they mean a little bit more for a systematic failure. In doing so, the focus on systematic definition should be made resulting in a safe, practical interpretation. So looking at the 61511 definition, what besides changing the process or the documents or the design, what really stands out now is that there's a pre-existing fault which occurs in random conditions. So we're going to take a closer look at what that actually means. So a systematic failure will cause an increase in the probability of failure on demand, just like any random failure, as particular conditions can be modeled in the same way. Thus, it is essential that all failures be included in a failure rate analysis. And we will understand what all of that means later on. But for now, remember that systematic failures will continue to occur until they are effectively addressed by design changes, by process improvements, by better training or better documentation, better reviewing, better testing. Systematic changes, there has to be something that is improved upon. And until that improvement is taken into consideration and you retest or you redo the documentation, making sure that this problem isn't going to pop up again, it needs to be counted in failure rates because it will keep happening until it is properly addressed. So some tend to classify many real-life failures as systematic. And in doing so, they end up with very low and unrealistic random failure numbers. And we think that that has a lot to do with the blurred line of what is random and what is systematic. And it's simply not defined well. It should always be the objective of any failure data collection program to collect all of the information on all of the failures and count all realistic failure rates as random until it is absolutely proven that systematic changes have been eliminated in any future failures of a given type. So until you know that your changes affect that systematic failure in a positive way, you need to count that systematic failure as random. And then once you've changed the documentation or the design, you've changed the material that wasn't quite working out, you've had multiple batches go through, you made sure that it's not going to have the same issue, then count it as a systematic failure. So I learn best from looking at real-life examples. And I thought we could do that today to really make this all sink in. When I'm going to first read a scenario and ask you, is it random or systematic? In doing so, I will open up a poll and ask you to answer. And I can't see what anybody is, who voted for what. I can't look that up. It doesn't really matter to me. But we sent out 15 questions to a mailing list, and we chose 3 of the 15 to show you today. We sent out the survey, and we had a bunch of answers come in. And I'm going to compare our answers to the survey that we did and see how real-life examples could possibly be problematic. Or you can see how many companies in different locations have different definitions of what is random or what is systematic. So for the first example, we're going to look at a flood alarm system failed to enunciate high water levels in an industrial process such that an orderly shutdown could not occur and electrical power was not disconnected. This resulted in significant equipment damage beyond the normal cleanup cost. The problem was traced to a trip point being set too high. However, the trip point was set exactly as stated in the calibration procedure. An error had been made in the calibration procedure as provided by the system designer. This error had not been detected during installation and commissioning, nor during several years of operation. So we sent this out to our mailing list and asked the survey participants to decide if this should be categorized as random or systematic. And this is the easiest of the 3, so we'll start you off with an easy one. And I'm going to launch this. And you should be able to see the poll, so if you can go ahead and, okay, we have some votes coming in. Great. Is there anybody else going to vote? Oh, there we go. Okay, we got most of the votes in. I'm going to close this and show you what our webinar voted. So as you can see, most people thought that this was a systematic failure. A few thought it was a random failure. Compare that to the survey that we sent out, and as you can see, a few people thought that it was not a failure. About 40% thought it was a systematic failure, and 57% thought that it was a random failure. So our webinar had a more clear direction that people wanted to head, but that, as you can see from the survey answers, there's not necessarily black or white. This is not a cut and dry definition or even example. And these are real world examples that we're looking at, so we can understand how it could be quite confusing. So let's break apart the question and see what you should concentrate on and what you should look at here. So the main problem was that the trip point was set too high. So the first question you should ask yourself, would this failure still have occurred if procedures were corrected? Probably not. No, the failure was simply made by the incorrect information stated in the document. Okay, so if this failure was classified as systematic and not included in a failure count, would that count be dangerously optimistic? No, I don't think so. The calculated dangerous failure rate would be considered fine if the problem has been corrected. So if the problem has not been corrected yet, we would consider this a random failure. But if the document has been changed, if there has been some time that passed and people have been setting that trip point to the correct procedure, to the corrected procedure, then that error would no longer happen. So if all of that has been taken care of and you have proof that this was just because of the procedures, it is taken care of, will not happen again, then it is a systematic error. And you can count it as such. You do not need to count it in your failure rates. So the procedural document was the issue that can be fixed by correcting the procedure itself. This document should be, this failure should be included in any failure report used for probabilistic analysis for this product until it has been determined that the issue has been corrected. Okay, so now let's take a look at some harder questions. Next, we're going to look at a failure occurred when a de-energized to trip remote actuated valve closed and shut down the process during normal operation. The failure was traced to a PLC logic solver rated to 50 degrees C, where an output module failed de-energized. A component in the output module, a transistor, had failed such that it could no longer conduct current. The ambient temperature was hot. It was 55 degrees C. They did an X-ray of the transistor to see what happened, and it showed a burned out bond wire, likely due to an electrical overstress. So I'm going to open up the polls again. So do you consider this failure random or systematic? Now if you go ahead and vote again, if this was random or systematic. Once and again, I cannot see who voted what, so it doesn't matter if you're right or wrong. This is just for education. Okay, we have a good portion of the votes in. Great. So I'm going to share with you what our webinar saw it as. And as you can see, 43% of the people in the webinar said this was a random failure, and 57% said systematic. So it's not something, we're pretty evenly split. It's not something that can say, oh, it's definitely random, or oh, it's definitely systematic. So we'll take a look at what our survey said. And our survey was kind of flip-flop. It said 39% of people that took our survey thought it was systematic, where 57% said it was random. So once again, you can't really say there was a clear direction either way. So let's break apart this question. So X-ray of the transistor showed a burned out bond wire, likely due to an electrical overstress. So the first thing that we want you to ask, would this failure still have occurred if the temperature had been 45 degrees instead of 55? Actually, it probably would have, because the failure was caused by an electrical overstress. So if this failure was classified as systematic and not included in the failure count, would the count be dangerously optimistic? Probably. The calculated dangerous failure rate would be too low. This would need to be a random failure and counted in their failure rate. And the explanation is this is a real random failure, although some argue that it should be classified as a systematic failure because the actual temperature was greater than the specification, that factor did not cause the failure. This failure should clearly be included in any failure rate used for probabilistic analysis for this product. So we don't care if you call it random failure or if you call it systematic failure. The main bottom line is that it needs to be included in the product failure rate. So for the last question we have, a maintenance technician routinely checks and adjusts the trip point on a motor shutdown relay. The procedure for checking and adjusting the relay were all correct. All personnel were well trained in the procedure, and the failure occurred when the mistake was made with the adjustment. The trip point was set too high and the motor was not shut down to maintain safety. So once again, I'm going to open the poll, and would you consider this a random or a systematic error? Okay, the votes are coming in. Okay, we have a good portion of them in. Let's close it, and I will show you. There we go. As you can see, 42% of our webinar users think that this should be a random failure, when 58% said this should be a systematic failure. So now let's compare that to our survey. And we were very, very close to our survey results, where 57% instead of 58% said systematic and 43 instead of 42 said random. So what are the sticking issues here? So first of all, what pre-existing fault has occurred? Well, there's no really pre-existing fault that's clearly given. The procedures were correct. The people that did the maintenance routine checks were well trained. What happened? Well, sometimes people make mistakes. Sometimes people have a bad day, or they're thinking about something going on at home and their head's not completely focused at work. It's not always something that you can prepare for. So the next thing, what procedure could have been enhanced so that this could be a different situation or this failure not happen again? Well, an argument could be made that a new procedure is needed where a second person checks every adjustment, and when the maintenance budget is doubled, those changes can be made and handled. But the procedure was correct and people were trained correctly. Just sometimes people are people. They're not perfect. They're humans. They make mistakes. So until there is a buddy system or a double check procedure in place, this failure needs to be counted as a dangerous field failure. So whether you want to call it a random or systematic, that doesn't matter. The main point is it's included in the safety failure rate calculation. So per our vocabulary, we would call this a random failure until new procedures are established and proven. So this failure clearly needs to be in any failure rate and used for probabilistic analysis at this site. And that brings up a good point that there could be different sites within the same company that have different ways of dealing with random versus systematic, different definitions of dealing with random versus systematic, even different maintenance. So there is something that we highly recommend called the Site Safety Index. And this is a model for the probability of a site-specific error that impacts the failure rate. So the Site Safety Index model is a simple approach based on concepts from IEC 61508 to more accurately account for site-specific operational practices. So this approach allows a site with a strong safety procedure to take credit for that accomplishment while not masking issues at other sites. So if you have your company's going through, they're doing all of the right things, they're really trying hard, and they're mostly getting there. But you have a sister company that their maintenance is a joke. Those are things that you don't want to be penalized for their issues, but you don't want to cover up if they're going to have dangerous failures in their devices. So what do? You create a Site Safety Index model, and there's several different factors that have been identified thus far which impact the Site Safety Index. And these could be a combination or just a few of these, but you want to look at the quality of the equipment selection and the qualification, the commission testing, the quality of safety validation tests, proof test procedures and documentation, failure diagnostics and repair procedures, device useful life and tracking and replacement process, the SIS modification procedures and decommissioning procedures, and a bunch of other things can be involved in the Site Safety Index model. So when you're evaluating yourself for the Site Safety Index, those are all things that you want to keep a mental note of. So to be in the Site Safety Index model, there's 5 different levels. Level SSI 0 through level SSI 4. And these are all models in Excelentia that you can see what the difference between SSI 0 to SSI 4 would be. So let's take a look at SSI 0 first. What is your maintenance? What is your site safety? Well, hopefully none of you are in this boat, but what if you have none? What if something breaks? Repairs are not always done. Testing's not always done. What about the equipment is not replaced until there is a definite failure? Equipment is selected according to history and nothing else. Electrical power supplies may drop out and have transient voltage spikes and surges. Pneumatic supplies and hydraulic fluids are sometimes kept clean, sometimes not. So those are all things that could affect you to be an SSI 0. But knowing the people that attend these webinars, the people that are trying to do the right thing, I have a feeling that none of you are SSI 0 and do nothing. So there's a much better chance that you are a medium site safety plant or a good site safety or even an almost perfect. Let's look at what an SSI 4 or a perfect site safety would be. And that would be if repairs are always done and done correctly. Testing is always done correctly and on schedule. Equipment is always replaced before the end of useful life. Equipment is always selected according to the specified environmental limits and the process compatible materials. The electrical power supplies are clean, of transient and isolated. The pneumatic supplies and hydraulic fluids are always kept clean and it would never become dirty. And this level is generally considered not possible, but retained basically for a model for comparison. And why is that? Everybody strives to do well, but chances are you're not going to be perfect at everything. You know, I certainly am not perfect. If any of you know my husband, please don't tell him I actually admitted to this, but most of the time, I'm not going to be perfect at everything. Every human I've ever met is not perfect at everything. And that's kind of the SSI 4 level. You are in a condition that is so much better than everybody. You always do everything perfect. That's just not realistic. So hopefully you're also unrealistic as SSI 0. So you will fall somewhere in between the 1, 2, or 3 level. So what all is impacted by these site practices? Well, your failure rates for each product would be impacted. Your actual proof test intervals and proof test effectiveness, the actual mean time to store, and the probability of initial failure. So what happens when you're looking at field failure rates according to SSI levels? So as you go down the SSI level closer to 0, your failure rates are going to be increasing. So field failure studies where we collected and studied billions and billions and billions of unit operating hours here at Exida. And we've actually found that failure rate multiplication factor between 2 and 4, depending on the product type, when comparing SSI 0, or no maintenance whatsoever, and SSI 4 as I'm always perfect, I never do anything not perfect. So they could be 2 times, 3 times, and 4 times, depending on where you fall. So that could be a big difference in failure rates from site to site. Even within the same company, you could have a different failure rate from site to site. So as advice, when you're looking at SIL verification, we suggest that any safety lifecycle tool that automatically updates failure rates used for PFD average calculation automatically should be avoided. So failure rates used for SIL verification should never be just automatically modified without an expert review of the data collection process. The review makes certain that no failure were excluded because they were wrongly classified as systematic or just thrown out of the failure rate calculation without double checking, making sure that everything was taken into consideration and that the problem has been corrected. As you can see, in these polls that we did, not everybody in this webinar, let alone everybody else that we did sent the poll out, there was not one single question out of the 15, I believe it was, or 16, that we had a unanimous decision. So there were always companies or people in companies that would say something's random or something's systematic. So here's the last slide. I have my email. I'm going to look at some questions in the meantime. If you think of questions later on, please feel free to email me. I also have a link to the reference material, our books, our site index, so you can take a closer look at all of those definitions, and safety blogs and previous webinars. Most of these are just statements, so let me go through them. Okay, here's one question we have. SSI addresses operation and maintenance on site. What about systematic failures that occur at the manufacturer or designer developer portion of it, for example? When we certify, we work with manufacturers also here at Exida, and when we certify their process, we ask for all of their procedures, their modification, and we audit their quality per SIL 1, 2, or SIL 3. We also ask for their field failures report and their shipment report. So we compare and go through, and we go through each of their field failure to classify if we would deem something as systematic or as random, that expert opinion. And if it is a systematic error on the manufacturers and it has been addressed and time has proven that it is no longer an issue, we then no longer count that as a random failure. But say there is a systematic failure, which is by definition systematic failure, yet it has not yet been addressed, we keep that in to compare what their proven in use history compared to the FMEDA failure rate is. Okay, and then another question. Oh, that's more of a statement. Okay. Well, if anybody has any other questions, please feel free to email me whenever you get a chance. And thank you for your time today. I hope you have a wonderful evening or morning, depending on where you are. Thank you very much.